good afternoon. This is Mrs. Crumbliss. Today we're going to do notes on limiting and excess stoichiometry. Please make sure you have your note packet out so you can fill your notes in as you go along. So when we have chemical reactions happening, we don't always use both of the reactants up completely. Oftentimes there's reactants that are left over, and there's one that's completely used up. The one that's completely used up is called our limiting reactant, and it's the reactant that's always completely consumed, and it's the reactant that determines the amount of product that's produced. So it always lets us know how much we're going to have when we're done. And when that limiting is gone, our reaction stops. So our reaction continues until that limiting is completely used. Our other reactant is called our excess reactant. This reactant isn't completely used during the reaction. There's always some left over when the reaction is complete. And it's added in excess on purpose to make sure that the limiting is used. And this is usually cheaper and easier to recycle. So you usually will pick your excess for a reason because it's easy and cheap to recycle, and your limiting will be your more expensive, less environmentally sound kind of reactant. When you do these calculations, you need to remember it's nothing more than a stoichiometry problem. You're just doing stoichiometry. You're just solving from one thing to another. The problem is going to usually contain the mass of both reactants because you need to figure out which one is actually going to run out first. You're going to convert the mass of each of the reactants to the mass of the same product. If you're not calculating for the same product, you're not going to get a good idea of how much you're going to make. And whichever reactant produces the smallest mass of the product is your limiting reactant. So whatever produces the smallest mass of product is the limiting reactant. And the other reactant is going to be in excess. Okay, so let's try our first problem looking at limiting and excess. So here's what these problems are going to look like. It says if 5 grams of aluminum reacts with 5 grams of hydrochloric acid, how many grams of aluminum chloride are produced? What is the limiting reactant and how much excess remains? We are not going to worry about this how much excess remains right now. So we're going to cross that part out, and we're only focused on what is our limiting reactant. And now we need to go look at our problem and figure out what do we have. So we know that we have 5 grams of aluminum, we have 5 grams of hydrochloric acid, and we want to know how many grams of aluminum chloride we have. So we're ultimately solving for grams of aluminum chloride. So I'm going to do this in 2 separate problems because I have 2 separate reactants going on. So for my first reactant, I'm going to start with grams of aluminum. Whenever I have grams, I convert it to moles. So I'm going to go to moles of aluminum. To do this, I'm going to use molar mass. Then I'm going to convert my moles of aluminum to moles of aluminum chloride. And I'm going to use my mole ratio. And then I'm going to go to grams of aluminum chloride using molar mass. So let's go ahead and fill in my picket fence. So I know that I'm starting with 5 grams of aluminum. 1 mole of aluminum, I'm going to look at my periodic table, is 26.98 grams of aluminum. My grams of aluminum cancel. Now I'm going to look at my balanced equation. There's 2 moles of aluminum in my balanced equation and 2 moles of aluminum chloride. Moles of aluminum cancel. Now I need to get to grams of aluminum chloride. For every 1 mole of aluminum chloride, I have some number of grams of aluminum chloride. I'm going to need to get that number from my balanced equation or from my periodic table. And my periodic table is going to tell me that it's 133.33 grams of aluminum chloride. And when I put that all in my calculator, I get 24.709 grams of aluminum chloride. So I know how much my first reactant yields. How much does my second reactant yield? So I'm going to do the same process. I'm going to start with grams of hydrochloric acid. I'm going to convert that to moles of hydrochloric acid. I'm going to use molar mass. I'm going to then convert my moles of hydrochloric acid to moles of aluminum chloride using my mole ratio. And then I'm going to convert to grams of aluminum chloride using the molar mass of aluminum chloride. So I'm starting with 5 grams of hydrochloric acid. My molar mass is always equal to 1 mole, so I have 1 mole of hydrochloric acid is 36.46 grams of hydrochloric acid. Grams of hydrochloric acid cancels. There are 6 moles of hydrochloric acid in my balanced equation to 2 moles of aluminum chloride. So now I'm at moles of aluminum chloride, and what's nice is I already know my molar mass of aluminum chloride because I did it in the first problem. So I just need to rewrite that down here. For every 1 mole of aluminum chloride, I have 133.33 grams of aluminum chloride. And when I put that into my calculator, I have 6.0948 grams of aluminum chloride. So my limiting reactant is going to be the one that makes the least amount of aluminum chloride. So my least amount of aluminum chloride is that 6.09. So that means my hydrochloric acid is my limiting reactant. My excess is my aluminum. And my amount of aluminum chloride I actually get is 6.10 grams of aluminum chloride. So that's my answer to the correct significant figures. And I now have to put that chemical formula on the end so that I know that you know what you're talking about. Okay, so now let's move on to this next part. This next part says how much excess remains. So we've already figured out what the limiting reactant is. Now we need to know how much excess remains. And to figure out how much excess remains, we have to know what our limiting is. Our limiting reactant is our hydrochloric acid, and our excess reactant is our aluminum. Oh, I already had this written on here, so let me erase that. First, we need to know how much of our excess was used. So that's the important thing that we're trying to figure out. How much of our excess was actually used? So how much of our aluminum was used? And to do that, we need to solve from our limiting reactant to our excess reactant. So we're going to start with our limiting, which is our hydrochloric, and we're going to solve for the excess. So we're going to solve for the aluminum, and that's going to tell us how much aluminum was used. So we're going to start with grams of hydrochloric acid. We're going to go to moles of hydrochloric acid, moles of aluminum, grams of aluminum. And this is going to equal aluminum used. So we have 5.00 grams of hydrochloric acid. And one thing that's really nice about these problems, we've already used all of these chemicals, so we already know all of the masses. So for every 1 mole of hydrochloric acid, I have 36.46 grams. There's 6 moles of hydrochloric acid in my balanced equation for every 2 moles of aluminum. And then for every 1 mole of aluminum, I have 26.96 grams of aluminum. And after I put that in my calculator, I have 1.23315 grams of aluminum, and that's how much was used. But it's asking me for what remains. So to figure out what remains, I need to take how much I started with. So I started with 5 grams of aluminum was my starting mass. I'm going to subtract the 1.2335 grams of aluminum that I used. And that difference is the aluminum that remains. How much aluminum that was left over when I was all done with my reaction. Now I need to give that answer in the correct significant figures. Because it's a subtraction problem, I'm going to answer to the hundredths place. So this is going to be a 3.77 grams of aluminum remains. And we want to know how much remains, because what if we want to use it again? Just like if your mom is making s'mores and she wants to know, well, how many marshmallows did we have left, so I know how many candy bars to buy next time to use up all the marshmallows. So that's kind of the idea of why you figure out how much remains. And I forgot to go forward, but it says, how do we solve for how much remains? Okay, so here is another problem. So this one says, how many grams of hydrochloric acid can be produced by reacting 10 grams of hydrogen with 20 grams of chlorine? How much excess remains? So remember, we start by just figuring out what's our balanced equation, what's our limiting, and then how much excess remains. And I already wrote the molar masses on here. So let's read our problem and look for our reactants, and our products. So it says how many grams of hydrochloric acids can be reduced. So this is going to be a product by reacting hydrogen gas, that's a reactant, and chlorine gas, which is our other reactant. So that means that I'm going to have hydrogen plus chlorine, which is going to give me hydrochloric acid. So H2 plus Cl2 gives me HCl. So there I have my balanced equation. And what I would like you to do right now is pause the video a second and try to work through these problems on your own. You have your balanced equation, you have your starting values, you have all the molar masses. See if you can fill it in and then hit play on the video again, and then you can watch me walk through it. Okay, so hopefully you did that on your own. And now we can walk through it together to make sure that you worked it correctly. So I'm going to start with my first problem being my 10 grams of hydrogen gas, and I'm looking for my grams of hydrochloric acid. So for every 1 mole of hydrogen gas, I'm going to have 2.02 grams of hydrogen gas. For every 1 mole of hydrogen gas, I'm going to have 2 moles of hydrochloric acid. And for every 1 mole of hydrochloric acid, I have 36.46 grams of hydrochloric acid. I'm going to make sure everything cancels, which it does. And this gives me 360.9900 grams of hydrochloric acid. If I look at my second reactant, which is my chlorine, I'm going to start with 20 grams of chlorine. I'm going to convert that to moles of chlorine. For every 1 mole of chlorine, I have 70.90 grams of chlorine. For every 1 mole of chlorine, I have 2 moles of hydrochloric acid. And for every 1 mole of hydrochloric acid, I have 36.46 grams of hydrochloric acid. When I do this, I'm going to get, oh, no, it's 0. 20.5698 grams of hydrochloric acid. So the one that gives me the least amount of hydrochloric acid is actually the one that had the larger mass. So you have to be really careful not to assume that the mass is going to tell you which one is in the higher amount and which one is in the lower amount, because that doesn't take into account mass or mole ratios or any of the other things that we need to look at. So our limiting in this case is going to be chlorine. Our excess is hydrogen. And our hydrochloric acid produced is going to be 20.6 grams of hydrochloric acid. So now we need to figure out how much excess remains. Remember that our chlorine is our limiting and our hydrogen is our excess. And we're going to start with our limiting and solve for our excess. So we start with 20 grams of chlorine, and we're going to solve for grams of hydrogen, which is going to be hydrogen used. So for every 1 mole of chlorine, I get 70.90 grams of chlorine. For every 1 mole of chlorine, there's 1 mole of hydrogen. And for every 1 mole of hydrogen, there is 2.02 grams of hydrogen. When I put this into my calculator, I get 0.5698 grams of hydrogen used. I want to know how much remains, so I need to start with the 10 grams of hydrogen, and this is our starting value. I need to subtract the 0.598 grams of hydrogen used, and then this is going to tell me that I have 9.43018 grams of hydrogen remaining. I need to answer this to the correct significant figures, which, because I have a subtraction problem, it's going to be to the 10th place. So this is going to be 9.4 grams of hydrogen remain. So now we're going to talk about percent yield. So percent yield is looking at how much do we actually get in the lab. So what we've been doing so far is a theoretical yield, and it's the amount of product you should get if the reaction goes perfectly, and it is what we've been calculating on paper. So all of these calculations we've been doing are just the theoretical yield. But when we do this in the actual lab, we often get different values, and that's the actual yield. And it's the amount of product that's the result of performing the lab. There are multiple reasons why these two amounts are different. And those reasons could be things like side reactions, reactions stopping before completion, and impurities. So those side reactions are things inside the container reacting that just happen for a moment or we don't really expect. Kind of like when we had the reaction in the reactions lab where it became carbonic acid, and the carbonic acid broke down into carbon dioxide and water. That's a side reaction. It's a reaction that we don't necessarily predict, but it happens, and it kind of makes things in the reaction a little goofy. Reactions don't always go all the way to completion. Sometimes they run out of energy before they complete. And impurities can be things like just things in the water in the solution. Like the water that we have here has a lot of metals in it from the pipes. And those metals cause there to be extra metallic ions in the water, which can cause reactions to happen that we are not intentional. So you aren't necessarily responsible for these three things, but just realize that the reasons why this happens isn't because your buddy spilled it while you were in the lab. That's like a human error. These are errors that we can't fix. They just happen inside our container. So here's your formula for percent error. The percent error formula is the actual yield over the theoretical yield. Your actual yield is your yield from the lab experience. Your theoretical yield is what you calculated, or your paper yield. I like this formula because it's alphabetical. A over T, actual over theoretical. I find that very easy to remember. And then you multiply it by 100, so it's in a percent. So when we do percent yield calculations, percent yield problems will have at least two masses given in the problem. So just like our limiting excess will have two masses, our percent yields will have two masses. At least one of the masses will be of a reactant, and one of the masses has to be the product. The mass of the product has to be given to you. That's how you know how much was produced in the lab. The problem will typically read something like, when blank grams of A reacts with B, blank grams of C was produced. So there's like nothing to fill into those blanks. Just realize that that's kind of the format of what these problems typically will look like. So when we look at these, here's an example. We have 45.8 grams of potassium carbonate that's going to react with excess hydrochloric acid. 46.3 grams of potassium chloride are formed. Calculate the theoretical yield and the percent yield. So we're going to do two different calculations in this problem. First thing we always need is balanced equation. So when we balance this equation, we have potassium carbonate reacting with hydrochloric acid. So we have K2CO3. You should recognize that these are both compounds. So this must be a double replacement reaction. We know that one of our products is potassium chloride, and our other product is going to be the hydrogen and the carbonic acid, or the carbonate ion. When you do this, you should recognize that that carbonate ion is also aqueous. So how does this reaction even happen? If you remember back to when we did our reaction lab, carbonic acid doesn't exist for very long, and it breaks down into carbon dioxide gas and water. So because this made a gas and a liquid, the reaction does happen. So now I can balance this because I have a gas and water on my product side. I have my reactants, and all I'm going to need to do to balance this is put a 2 in front of my potassium chloride and a 2 in front of my hydrochloric acid. So my starting units are going to be my grams of potassium carbonate, and my ending units are going to be the grams of potassium chloride. The other thing I know is my actual yield. So this is what happened in the lab. So someone in the lab did this reaction and got 46.3 grams of potassium chloride. So I'm going to need that in my percent yield portion of the reaction. But that's going to be for that second calculation. So I'm going to start with my grams of potassium chloride. Okay, so let's fill in our picket fence. So I'm going to start with my grams of potassium carbonate, which is going to be 45.8 grams of potassium carbonate. Remember that I'm solving for grams of potassium chloride. I'm going to convert this to moles. So for every 1 mole of potassium carbonate, I'm going to need to look on my periodic table to get the mass of potassium carbonate, but that's 138.21 grams of potassium carbonate. And then I'm then going to look at my balanced equation, which for you is above. If for me it's on the other slide, but I have it in front of me. For every 2 moles of potassium carbonate, there's going to be, I'm incorrect. There's 1 mole. I looked at the wrong number. Let me fix that. For 1 mole of potassium carbonate, there are 2 moles of potassium chloride. Now I need to get to mass of potassium chloride, and every 1 mole of potassium chloride is going to give me 74.55 grams of potassium chloride. So now I'm going to put this into my calculator. It's going to give me 49.4 grams of potassium chloride, and this is my theoretical yield. In a perfect world, that's how much potassium chloride I would get. So now I'm going to calculate my percent yield. I'm going to take my actual yield, which was given to me in my problem, because it has to be. It's going to be my lab value, which is 46.3 grams of potassium chloride. I'm going to divide that by my theoretical yield, which is 49.4 grams of potassium chloride. I'm going to multiply that by 100, and I'm going to get 93.7%. And that tells me that I got 93.7% of the potassium chloride I expected to get. Okay, so let's look at the last problem. So here we go, the last problem. Aluminum oxide was prepared by heating 225 grams of chromium 2 oxide with excess aluminum. 100 grams of aluminum oxide was obtained. Calculate the percent yield. I would encourage you to pause the video and try to do this one on your own, and then play the video and see how you did. This is when it's good to make mistakes and to see if you know what's going on. So the first thing we need is our balanced equation. Our balanced equation is going to be chromium oxide plus aluminum. It's going to be a single replacement reaction because I have a compound and a singular element. I'm going to balance these. My starting unit is going to be my grams of chromium oxide, and my ending unit is going to be grams of aluminum oxide. And I know that there was 100 grams of aluminum oxide as a theoretical yield, or actual yield. So now to fill in my picket fence, I'm going to add 225 grams of chromium oxide. I have 68.0 grams of chromium oxide to 1 mole of chromium oxide. I have 3 moles of chromium oxide to 1 mole of aluminum oxide. I have 1 mole of aluminum oxide to 101.96 grams of aluminum oxide. I'm going to make sure everything cancels. And I'm going to get 112.455 grams of aluminum oxide. And then I'm going to put that in my calculator. Or no, I'm going to put that, get my percent yield. So my actual yield is 100 grams of aluminum oxide. My theoretical yield is 112.455 grams of aluminum oxide. And this is going to give me 88.9% yield. So that is all the notes we have on this. Please make sure you answer the questions that are in Schoology after this video. And then you can pick up the extra practice packets from the sub. There's one with a little more guidance and one with a little less. Choose the one that's going to work best for you. Have a great day.